Hello, I'm Ahmed Arashi, and in linear modeling, I want to discuss about statistical inference. Specifically, we want to consider hypothesis testing and confidence SAS. Before going through the utilities or explaining about pivotal quantities in order to construct confidence intervals or sets and conducting hypothesis testing, I want to give a little bit of theory which is needed as preliminary results. Let's start with some lemmas. In statistics, quadratic forms play important role, specifically if the variates are normally distributed. So here we have some sort of lemma. I will give these lemmas without proof. Suppose that x has the vector x of p-dimensional has normal distribution, zero mean, identity matrix, and also A is a symmetric and idempotent matrix of dimension p, which the rank of A is equal to R. So it is symmetric and idempotent. Then we can conclude that if we define S as x prime ax, it has chi-square distribution with r degrees of freedom, which r talks to the rank of A. This is an important lemma which we can construct other lemmas based on it. Let's consider the second lemma. Suppose that x is a p-dimensional vector, has normal distribution, zero mean, identity matrix, and similar to the first lemma, we define S as x prime ax. A is negative definite, and we also have vector y, which is defined as a matrix B pre-multiplied by x. If B times A, pre-multiplying A with B is equal to 0, then we can conclude that S is independent of Y. Here I use this notation, independent. This lemma also plays an important role in the rest of theory. And another lemma which comes from the first lemma, if in general we assume that x has normal, is a p-varied vector, has normal distribution with general mean vector mu and variance covariance matrix sigma, then we can conclude that x minus mu transpose sigma inverse x minus mu has a chi-square distribution with p degrees of freedom. Note here that if the covariance matrix is sigma, then you have sigma inverse here. And we can also consider, according to lemma 1 and lemma 3, we can consider, let's write it this way, lemma 1, lemma 2, and then lemma 3. We can, let's say, define a z vector, something like minus half x minus mu. And simply we see that the term that I've defined here, I can write it as z prime z. But before that, if I consider the distribution of z, it is, of course, it's a linear transformation of x. X has normal distribution, so z has normal distribution. The mean is equal to 0, and the variance covariance matrix is, let's just compute it. The covariance of z is the covariance of sigma minus half x. Sorry, you can just keep leave it here. Sigma minus half the variance covariance matrix of X, and then sigma half, which is equal to identity. So it is identity. And based on the first theorem, we can then write it as Z prime Z, which the A matrix here is equal to identity matrix. Okay, if I have A here, it is now equal to identity matrix. And according to this first lemma, if A has rank equal to R, then this quadratic form has chi-square distribution with R degrees of freedom. However, here A is IP, and the rank is equal to P, so we have P independent columns. So I can decide that this is equal to this quadratic form has chi-square distribution with P degrees of freedom. And interestingly, you can write this expression as Z prime Z. So you see, in one hand, I proved theorem lemma 3 based on lemma 1, and we're gonna use lemma 3 and lemma 2 in our derivations. Just as an illustration, let's add another page. Just as illustration, let's see what we can do with this lemma. For instance, if we have the expected value of y equal to eta and the covariance of y equal to sigma square identity, for a moment assume that it is of dimension n. I want to take you through, linear modeling, so we usually assume that the response is n-dimensional. So I can write or better say construct this quadratic form y minus eta transpose the variance covariance matrix inverse, and then y minus eta. So based on theorem 3, you can conclude that it has, or better say lemma 3, it has chi-square distribution with n degrees of freedom. And if I just simplify it, you can write it this way: y minus eta transpose y minus eta, and it has chi-square distribution with n degrees of freedom. However, this is not the target. We want to see the distribution of sum of squares of errors, or we want to see the distribution of sum of squares of best estimators. In this case, we can say, okay, suppose that E is a matrix in which the columns are in VE, the error space. So assume that it is of dimension n minus r times 1. It then and also assume the distribution is normal. Here y has a normal distribution, so everything here from now on is based on normality assumption. So it has normal distribution with 0 mean. Y is 0 because the expected value of y is equal to xb, and x is in VR, e is in VE, and those are mutually orthogonal. So e prime xb is equal to 0. Just to show the expected value of a prime y is e prime, the expected value of y, then you have e prime xb, and this is equal to 0. So the mean is equal to 0, as I said. E is in VE and x in VR, the columns. You know that these two spaces are orthogonal to each other. So the mean is equal to 0, and variance covariance matrix easily obtained as by this formula. So if I construct a quadratic form, or better say sum of the squares of errors, it would be our interest to find the distribution of that in order to conduct inference. So once again, according to the previous lemma, the lemma 3, I have to subtract the mean and then the variance covariance matrix inverse. So I do the same thing. The mean is equal to 0, so it is e prime y transpose. The variance covariance matrix e prime e inverse, and once again e prime y. Okay, if you look at it, you can simply write it as y prime e prime e inverse e prime y. But this is nothing more than SSE. You know that it is SSE. Huh? This is SSE. This whole component here. Sorry, I must write it this way. The whole component is SSE. Huh? But interestingly, based on lemma 3, we can conclude that the distribution is chi-square with n minus r degrees of freedom, because the dimension of e prime y is n minus r. Huh? So we can easily conclude that SSE divided by sigma square has chi-square distribution when, with n minus r degrees of freedom. And this is an important result which we're gonna use it further on. Another thing which is important is the distribution of sum squares of best estimators. Now let's look at the best estimators. Let's look at t prime y. If you remember from Gauss-Markov theorem, when you want to estimate QB, you can use the best estimator b hat. So and you can then write it as t prime y. So the t prime y here, suppose as S-dimensional, once again normal distribution, t prime the expected value xb, and the variance covariance sigma square t prime t. Huh? And if I construct a sum of the squares, I can write t prime y minus the expected value. Once again, I'm using the third lemma, transpose variance covariance matrix inverse, and then the expression itself t prime y, the variate minus the expected value t prime xb. Once again, like above, in similar fashion, I can write it y minus xb transpose t prime. Sorry, I use small t, capital T. Sometimes it's I confuse a little bit. So it's small t to make difference. This capital T is for transpose notation. Inverse t prime y minus xb divided by sigma square. And then according to the third lemma, once again it has chi-square distribution with s degrees of freedom. These are actually the preliminary notes, and we want to use further on for a statistical inference. But what about lemma 2? We also want to use lemma 2 and see what we can get from lemma 2. Once again, remember that I have a quadratic form and linear transformation of x, which has normal distribution. If the A matrix times B or B times A is equal to 0, then S is independent of Y. Now let's see what we can do with that with respect to SSE. Of course, once again, if I just repeat the notation, I can write Y as in general form x minus mu according to the third lemma, and then you found out that y prime y has chi-square distribution with p degrees of freedom. So I can say, let's work with this guy, with e prime y. Let's work with this guy. I can take this variance covariance matrix, take the inverse of square root, and pre-multiply by e prime y in order to get the variance covariance matrix equal to identity to use the independency lemma. So I can write it as sigma square e prime e minus half and then e prime y, which has then normal distribution with zero mean and identity variance covariance matrix. Simply, if you take it as z, then z prime z has chi-square distribution. But you will see that if I do this, I will get the previous result, which talks to the above, and it is nothing than SSE divided by sigma square, which has chi-square distribution with n minus r degrees of freedom. However, if you consider t prime e prime e inverse e prime, it is equal to 0. Why? Because t is in VR, e is in VE, the error space, and those are mutually independent. So I can conclude that SSE is independent from the best estimator, t prime y. So this is the conclusion that we can obtain here. Now we can go to the inference, but I stop the video here and record the rest of the work in another video. Thank you.